In this video, I'm going to draw the Lewis structure for these molecules, and I'm also going to identify bond dipoles and the net molecular dipoles. To start, I'm going to draw the SO3 Lewis structure. The central atom with single bonds to all oxygens here. The next step is to start to fill the 24 valence electrons to the outer atoms. For those. We come across a problem as S is not going to suffice the octet rule. So what you have to do is call the resonance hybrid, where you give a partial bond to the S to all the oxygens, which will, as you add the 3 up, equals 1 full bond. So after you do that, you have all 24 valence electrons counted for, and the octet rule applies. The next step is to identify bond dipoles. Oxygen is the more electronegative atom, so it's going to have a partial negative charge, shown here. S is going to be positive. Go to each one, draw the negative, positive on the S, partial negative charges on all the oxygens, and the partial positive charge on S. The next step is to draw the molecular geometry. The molecular geometry of SO3 is trigonal planar, and all bonds are the same. The molecular dipoles are the same as the Lewis dot. Oxygen is still more electronegative than S, so positive S, negative O, and all bonds are the same, therefore there is no net dipole. And when there is no net dipole, the molecule is nonpolar. Let's move on to OF2. In this Lewis dot structure, there's 20 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. F is the most electronegative atom, so the electrons are going to drift towards it, which I've shown here: positive on oxygen, negative on F, partial negative charge, and partial positive. The molecular geometry of OF2 is bent. As you see here, we have the two bonding pairs on oxygen and two non-bonding right here and right here. There is a net dipole. As you can see, all arrows are pointed down, so the net dipole will be in the down direction. And because not all of the bonds are the same, this molecule is polar. Let's move on to BeCl2. This has 16 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16. Be does not follow the octet rule because it is an exception, and that is okay. The next step is to look at the bond dipoles. Cl is more electronegative than Be, so Be is going to have the partial positive charge, and both Cls will have the partial negative charges. Next, the molecular geometry of BeCl2 is linear, as there is no non-bonding pairs on Be. Because both of the bonds are the same, there's no net dipole, and this molecule is nonpolar. The next molecule we have is CCl4. There's 32 valence electrons, 8 connecting each C and Cl. Cl is more electronegative than C, so each Cl is going to have a partial negative charge, and the C will have the partial positive charge. The next step is to draw the molecular geometry, which would be tetrahedral. In this tetrahedral, all of the bonds are the same, and the molecular dipoles will be negative Cl and positive C. Because all bonds are the same, there's no net dipole, and this molecule is nonpolar. The last molecule we have is O3. There's no net dipole because the atoms are the same, where there's 18 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. Each oxygen follows the octet rule, so this is correct. The molecular geometry of O3 is bent, as oxygen has 3 domains, 1 non-bonding. Because of the non-bonding pair, not all domains would be the same, therefore causing it to be polar. Some common mistakes to watch out for is not applying the octet rule correctly, not remembering to remembering to correctly count valence electrons, and remembering the resonance hybrid for molecules like this.